Welcome to another deep dive, and this time we're going headfirst into the world of waves.
Love it. A world of waves.
Yeah, our listeners particularly curious about reflection, refraction, and diffraction.
Oh, great choices.
Yeah, and what's fascinating is that we're going to be using what looks like student notes and course specifications from a Scottish secondary school physics class.
You know, you don't always need a university-level textbook to grasp these concepts, right?
Exactly. It's amazing how much insight we can gain from even high school level physics. It can really unlock some cool secrets about the universe.
Absolutely. You know, the foundations are everything. Once you get those, you're going to see them everywhere. It's going to blow your mind.
So first things first, let's define what a wave actually is, because it's not like an object that's moving from point A to point B.
It's trickier than that, for sure. The key is energy transfer. Waves are how nature moves energy around without permanently displacing matter. It's more like, think of a surfer riding a wave. They're not being, carried across the ocean by the water. They're riding that energy pulse moving through the water.
That's a really, really good analogy. And speaking of different types of waves, our source material here talks about two main types: transverse and longitudinal waves. And they use the classic slinky example.
A classic for a reason. It works every time.
It really does.
So for longitudinal waves, think sound, right? The vibrations are parallel to the direction the wave travels. It's like if you squeeze a part of the slinky and let go, you see that pulse traveling.
Right. And each individual coil is pretty much staying put. It's just that energy moving through. So for sound, it's those compressions, like pulses of higher air pressure, that our ears are picking up.
Exactly. And then we have transverse waves, which are more like if you shake a rope, right? That wave travels down the rope, but the rope itself is moving up and down, perpendicular, not parallel to the direction the wave's going.
Right. So light waves and water waves, those are great examples of transverse waves.
Yeah. And it's this seemingly basic difference in how the energy's carried that really leads to these three phenomena you're so interested in: the reflection, the refraction, and diffraction.
Right.
They're just different ways waves interact with their environment.
And that brings us to wave parameters. We need
Yeah.
to talk about those and understand those behaviors. Wavelength, amplitude, frequency, period.
It sounds scary, but it's not too bad.
It's not that bad, but they all kind of work together, and that's where things get interesting.
Absolutely. So wavelength, let's start there. The distance between two corresponding points on a wave. Like,
Yeah.
Crest to crest, the peaks of those waves.
Okay, so like measuring the distance between two wave peaks out in the ocean.
Sure.
Got it. And then there's amplitude, the wave's height. Bigger wave, more energy.
Right, and the source material actually mentions tsunamis versus ripples. Quite a difference there.
Huge difference in energy there for sure.
Exactly. One can wipe out a city, the other one barely moves a leaf.
Right. Then we have frequency, which tells us how many waves pass a point in, let's say, 1 second.
Yeah, so higher frequency means more waves hitting you every second.
So more energy then.
Sometimes. Depends on the type of wave. Like high-frequency sound wave, that's going to sound louder, definitely more energy. But with light, it's more about higher frequency means shorter wavelength, and that means different colors.
So going from red light to blue light is kind of like going up in frequency.
Exactly. Each color, a different frequency of light, and it all boils down to those tiny wavelength differences.
That's pretty awesome.
It is pretty cool.
Then last but not least, we have the period, the time for one complete wave cycle. Kind of the opposite of frequency.
Longer period, fewer waves each second. And the cool thing, they don't just exist on their own. They all interact. It's all governed by the wave equation.
Ooh, equations. This is where the magic happens. But how does this equation help us actually understand how waves behave in the real world?
It's the glue that holds it all together. It's
Right.
like this. V equals phi. V is the speed, F is frequency, and the is the wavelength.
Okay, I'm following.
So say we have a light wave, right? We know its frequency and speed. We can use this to figure out its wavelength. Scientists use this for distant stars or sound waves to understand what things are made of.
So this one equation really unlocks a ton of information.
Totally. It's all about those relationships: wavelength, frequency, speed, even the period. They're crucial for understanding how waves act when they hit obstacles, change what they're traveling through, or even just moving through space. And this brings us back to those behaviors you mentioned earlier: reflection, refraction, and diffraction.
All right. Wave parameters, check. Wave equation, check. I think we're ready to dive into reflection, refraction, and diffraction. Let's see these wave behaviors in action.
Let's start with reflection. Maybe the easiest one to picture, like imagine you throw a tennis ball at a wall.
It bounces right back.
Exactly. It's, essentially what reflection is. A wave hits a boundary and bounces back. Simple as that.
Okay, so light bouncing off a mirror, sound echoing in a canyon. It's all about those waves hitting a surface, changing direction. But is it really that simple? Does the angle matter?
You're thinking like a physicist. The angle is key. The angle the wave hits at, we call that the angle of incidence. It's always equal to the angle it bounces back at, the angle of reflection. Perfect symmetry.
So if I shine a flashlight and mirror at, let's say, a 45-degree angle, the light beam bounces off at 45 degrees too.
Exactly. It's like a perfect rebound. And this works for any kind of wave, light, sound, even those water waves we were talking about earlier. It's physics in action.
Pretty cool. But what about the energy of the wave? Does some of it get lost when it reflects?
Good question. In a perfect world with a perfectly reflective surface, all that energy would be conserved. But in reality, some energy is always absorbed by the surface. Think of it like a tennis ball. It loses a little bit of its bounce each time it hits.
So a mirror doesn't actually reflect all the light that hits it. What happens to the energy that gets absorbed?
It can transform into other kinds of energy, often heat.
Yeah.
Ever touch a mirror that's been in the sun?
Yeah.
It's a little warm, right? That's the light energy becoming heat.
Okay, so reflection, it's all about bouncing back. Angle in equals angle out, but a little bit of energy loss in the real world.
Got it. Now, what about refraction? I remember the source material mentioned something about waves bending when they go from one material to another.
Right. It's like when light goes from the air into water, it slows down because water is denser, and this change in speed makes it bend. That's refraction.
Like a car driving from a smooth road onto a sandy beach. The wheels that hit the sand first slow down, making the car turn. Perfect analogy. And just like with that car, how much the wave bends in refraction depends on the angle it hits that boundary between the two materials. Bigger speed difference, more bending.
So if light goes from air into glass, which is even denser than water, it would bend even more.
You got it. And there's another cool thing about refraction. It doesn't just change the wave's direction, it messes with its wavelength too.
Wait, the wavelength changes too. What happens to it?
Well, since the wave slows down in the denser stuff, its wavelength gets shorter. Think of it like squeezing those wave crests closer together. But here's the kicker. Even though the wavelength changes, the frequency stays the same.
Hold on. The frequency doesn't change, but the speed and wavelength do. How does that even work?
Remember the wave equation, v equals. If speed changes, but frequency has to stay the same, then wavelength has to change too. It's all connected.
This is blowing my mind. So refraction makes the wave bend, changes its wavelength, but the frequency stays the same. Is this why a straw in a glass of water looks broken? I saw a picture of that in the notes.
You got it. Classic example of refraction. Light from the straw bends as it goes from water to air, and our eyes see it as broken.
Wave behaviors can make some pretty cool visual stuff. It's amazing.
Right. And refraction isn't just about illusions, it's how eyeglasses work, how contact lenses focus light, even fiber optics, transmitting data super fast.
Wow, I didn't know it was used for so many things.
Mhm.
Okay, last one, diffraction. We saw that picture of waves curving behind a harbor wall, kind of like bending around obstacles.
Exactly. Diffraction. It's all about waves spreading out after they go through an opening or around something, and it's most obvious when the opening or obstacle is close to the size of the wave's wavelength.
So a narrow opening causes more diffraction than a wider one, and longer wavelengths diffract more than shorter ones.
Exactly. Think of a big ocean wave. It easily curves around a small rock, but a short, choppy wave might just crash right into it. The longer the wave compared to the obstacle, the more diffraction you'll see.
Makes sense. And this is how we can hear someone talking around a corner, even if we can't see them, right?
Right. Sound waves have longer wavelengths compared to light. They can diffract around corners, so we hear things we can't see.
It's like a shortcut for sound waves. And it's got to be the same for radio waves. That's why we can get reception even with hills and buildings in the way.
Exactly. Longer wavelengths are better at going around obstacles. That's why AM radio, with its longer wavelengths than FM, can travel further, especially in tricky terrain.
So diffraction is all around us. It shapes how we hear things and lets us communicate over long distances. Are there other uses for it besides radio? I bet there are. I mean, it can't just be radio.
Oh, there's way more. Diffraction's used in all sorts of tech. Take X-ray crystallography. It's how scientists figure out the structure of molecules, like proteins or DNA. They look at how X-rays diffract after going through these crystal samples.
So they use how the X-rays bend and scatter to map out the atoms in the molecule.
Yeah, that's like a microscopic tool using diffraction.
That's amazing. So diffraction isn't just a scientific thing. It's a practical tool in medicine and other fields.
Big time. And it's not just X-rays either. Think about holograms, those 3D images that look like they're floating.
Oh, wow.
Those use diffraction too. It's the interference patterns from those diffracted light waves that give holograms their depth, make them look real.
I never would have guessed that. I mean, a simple wave behavior creating something so visually cool.
It's pretty wild, right? And don't forget about sound. Architects and sound engineers use diffraction when they design concert halls and auditoriums. They think about how sound waves will diffract around balconies, walls, all the structures in the space.
So they can make sure the music or the speech sounds good everywhere in the room.
Exactly. So yeah, diffraction is more than just a cool science fact. It's a tool used in so many different areas. From medicine to entertainment, it's all over the place.
This deep dive has been amazing. We went from basic wave stuff like parameters and wave equation to all this mind-blowing stuff about how waves behave, reflection, refraction, diffraction.
Yeah. And remember, we've only scratched the surface here. There's a whole universe of wave phenomena out there waiting to be explored. From tiny matter waves in the quantum world to those giant cosmic ripples, gravitational waves, it just keeps going.
I'm ready to learn more, that's for sure. So, to our listener, we hope this deep dive into the world of waves has sparked some curiosity. Who knows what other wave wonders you might discover out there?